welcome everybody. This is the first episode, I suppose, of our new podcast called Coffee Breakdown, where we hope to bring on a couple of fusion scientists from beginner to expert and everywhere in between to speak a little bit about not just their work, but their experiences inside not just fusion plasma science and research, but the scientific world in general. And our objective is to strengthen the connections between this scientific world and the general public through these types of discussions. It's our belief that the expression of the creative side of science is crucial to achieving this goal of building that connection. And in part, the practice of good communication skills are going to be very crucial to getting that access. So just keep in mind, everyone here, that this is a learning process, not just for everyone watching, but also for us here speaking about it. So my name is Aaron, if you don't know that, and we're going to introduce our first guest here, which is Michele Marin. I think we've had the luxury of being trapped in the same office for 4 years. So it's good to bring you on board just to also continue our history of discussions during the coffee break during our time together at doing our PhDs. So Michele Marin here is focusing on simulation of tokamak fusion plasmas, in particular the aspect of particle or impurity transport. So welcome, Michele.
Thank you.
Is there, I guess, anything about that you want to explain to us in any form or detail?
Yes, so I guess we're going to start a little bit with what I do and introducing the topic itself. So since this is the first episode, maybe it's a good time to do it. So we work on fusion, and in particular, probably at the beginning, it would be mostly magnetic confinement. The idea is we use magnetic field to confine the particles that are charged because they are high temperature. You have four states of matter. You have solid, liquid, gas, and then if you heat it even more, the electrons and the protons, they separate, and then they respond to magnetic fields. So you can use them to trap the particles. And then for a series of reasons, you might learn of them another time, but you use a donut shape magnetic field, and then that proved to be very successful in confining the plasma. So that's the basis of what we do. So then we heat this plasma to pretty insane temperature. The idea is you arrive around 150 million degrees, which is 10 times the temperature of the core of the sun. And from there, you start producing fusion. The fuel, which is deuterium and tritium, the two hydrogen isotopes, start to fuse and produce helium and a neutron. So in this system, you insert particles and heat, and then you will have plasma that is the most dense, the most hot, and also the energy needs to stay there for long enough for the particles to fuse. So we try to study how all of this plays out. And there's a lot of study, okay, I inject energy, and then how much time it stays there and how it transports inside the plasma. And then another part is particles. So the particles themselves will be injected inside, and then will slowly try to escape. And then one big question is, okay, how? So this is what I do. And the idea is, how do we study all of this? We build simulations. So we build giant computer codes, we just run them, and then we try to reproduce the experiment, so then we can try to invent new experiments or optimize and all the kind of things that come after that. So I guess The first part of my work was mostly just with multiple isotopes, so with hydrogen, deuterium, and tritium. That part is probably more important, but also more counterintuitive and technical. So I'm gonna talk about the second part,
Well,
which is more.
first, if I might ask, is just
Go
to
ahead.
throw this in there, is why is there the three different, like this hydrogen, deuterium, tritium? Why is it important to keep track of all three of them, or more than, let's say, one species in the first place?
Okay, yes. So um, in the fusion plasma, for experiments, we usually use a hydrogen because hydrogen doesn't fuse at all. So you have zero neutrons, and that's just convenient experimentally. But then when we will be in a fusion power plant, you want deuterium and tritium. So if you use just deuterium and just tritium, basically the cross sections, so the probability that the atoms will smash into each other is very low, or rather low. But then if you use deuterium and tritium, the probability is much higher. So ideally you want at every point a 50%, a mix where the deuterium and tritium are in equal amount. And
So,
then, go ahead.
so then it's important to capture, let's say, the ratios of these species inside the plasma. That's why it's important to simulate all of it, I guess, rather than just one and then proxying that it's going to be equal.
Yes, it would be. It is not necessarily. This ratio is not necessarily the same inside the whole machine. It could change, and you want to find kind of the optimum or how to maintain a ratio that makes sense, close to 50-50. If you go just a little bit away from 50-50, it's kind of fine. It's like a paraboloid, but the furthest you go, the further you go, the worse it is. So you kind of want to stay in that 50-50, and
Okay.
then you don't have just deuterium and tritium, you also have helium because you're producing it, and then it's staying inside the machine. And that might also be a problem. If you make too much helium, it can choke your reaction. So you have to be careful about the helium. And then you have impurities that are just, with impurities, we mean whatever is not deuterium and tritium, whatever is not fuel. So atoms will just be there because purity is impossible. Of course, the number of atoms is insanely large. So some atom of everything will be there. And then there will be quite a lot, and with quite a lot, I mean something between like 1% of something. Like beryllium, you often have 1%. And why do we have beryllium? Because the wall of our tokamak, which is this donut-like chamber, they are made of beryllium. So you usually have 1% of beryllium. And then you might have tungsten because there's the bottom part of the tokamak, which is called the divertor, which is made of tungsten. Then sometimes there's nickel or even impurities that you puff in yourself, like you inject impurities yourself in the plasma because they might help, for example, radiating light in the divertor region, which causes less heat flux to arrive in the divertor, and so the divertor doesn't break.
Yeah, right.
So
Because
there are a lot of
one of the issues is the material integrity, I guess, as the because that plasma has to exhaust its heat somewhere,
yes. So
right?
we need to exhaust the heat somewhere. In the largest experiment we have now is jet, and in jet it's kind of fine. So even if you have the maximum heat flux, you kind of have to protect your wall. They do a lot of puffing, and it's to keep the tungsten out mainly, but it's kind of still fine. I don't know of instances where the diverter got really hurt bad. But then with larger machines, the problem gets worse. ITER, just in steady state operation, will have a load on the materials which is higher than what any material can withstand. So you have to be a little smart on how you dissipate that. It's all doable. Like there are problems that can be solved, but you need to know that they are there and need to know a little bit on a few tricks on how to handle them.
Right. So you're saying that like if you puff in, I guess, these impurities or non-hydrogen species into the plasma, that helps to keep that diverter region cool. But then, of course, those impurities can then make their way, I guess, into the plasma where fusion is happening, right? So is that necessarily a bad thing, or what in your experience can you comment on that?
Yeah, so at the beginning, what we had was limited plasma, they're called. So basically, there's no diverter region on the bottom. There's just something, a piece of material, which enters in contact with the plasma. And then in that way, a lot of impurities get into the core. If the impurity content is too large, then impurities are bad. They're going to just destroy the reaction. They're going to dilute too much. They're going to radiate too much. And it's just going to be a bad time all around. When they introduced the diverter, at the beginning, the impurity, the main impurity was carbon, because at least at JET, and also in ASDEX. So these are different tokamaks that we have in Europe. And with carbon, the problem is that it dilutes the plasma a lot. So with 1%, let's say, of carbon, you have a 6% dilution. And then there's another parameter which is important in all the discussion, which is called Z effective. And it's basically the effective charge of your plasma. And that enters the turbulence in some way together with the dilution. So what you discover if you actually try to simulate on the plasma is that when you have impurities, kind of middle Z impurities, so carbon up to neon, maybe even argon, you're increasing the effective, increasing dilution, and the turbulence gets stabilized, which means basically that you can get away with a higher temperature. And so depending on the conditions, depending on your temperature, depending on which impurities you have, depending on a lot of things, this can be from really bad to not that bad. And actually, the last part of my work was with neon. And with neon at JET, it wasn't that bad. We saw that actually you could get the same neutron rate with and without neon. So that's a good thing in the sense, okay, we can get a lot of neon in the diverter, and even if it gets inside, it's still kind of fine. And the funny part, at least for me, in all of these, is that it's really situation dependent. So every situation with every different impurities will have a completely different outcome. And it's really difficult just to extrapolate what will be the optimal conditions in another machine. It's a really complicated and interesting problem.
Yeah, that's right. Because like what neon isn't that far from carbon, I guess, on the periodic table.
Yeah, it's 10 instead of 6.
Yeah, exactly. So they're quite similar if you look at the general, all the possible elements that could exist, but you're saying that their behavior in the plasma are very different.
Yes.
Well,
Well,
right.
it's not that the behavior is very different, but the amount of dilution and turbulence stabilization you get is different, and one ends up being bad and the other one ends up being good in some specific conditions. And then the problem we all have is we want to know what will happen in ITER, and we want to know what will happen in reactor. And you can't just say, okay, this is good in JET, and so it will be good in ITER. There's a plethora, like an insane amount of small details that could change the picture completely.
And I guess this is where the modeling comes in, right?
Yeah,
exactly. So
I think this is one of the real difficulties of our work in general, of the fusion community, that you can't easily extrapolate.
So I guess one of the questions is that if it's so difficult to tell what the plasma is going to do without simulating, or at least without having some simulation done on it, how accurate does the simulation need to be in terms of its impurity content, right? Like, do we need to get the exact species and its exact concentration correct? Or is there some room to play there, like that we can say, okay, if it's not exactly correct, it will still give us the same, roughly the same answer as if it were, right? Like, what sensitivities are there?
Yeah, so in my experience with these, you do have room to play, but you have much more room to play with trends than with absolute values.
Mm.
So you can say, okay, these will be good or bad in this condition, these particular conditions. And then if the experiment is kind of in that ballpark that you simulated, then it's going to be fine. Then the trend is going to be correct, probably.
So when you say trends, like what do you, can you give an example of like what is a trend that is that you notice that can also be applied then to designing plasmas, let's say?
Well, yes, I mean, this impurity business, it's kind of like that. We can say, so what we can say, for example, is regarding the core of the plasma, and the core of the plasma is a region that is inside another region called the pedestal. So basically, if you imagine your donut and you imagine a section of your donut is kind of a circle, let's say, the the outer part where it have contact with the material is like the edge. Then you have a region which is the pedestal, and then you have an inner region which is the core. And then if you use a model, okay, we'll come back to this because this is important, but if you use a model that it's not empirical and it's kind of based on fundamental physics, then you can say, and this model is able to reproduce the jet result, you can expect that it will also reproduce the ITER results, at least in the core. In the core, I'm talking about this region in particular because here we have decent models which are actually based on fundamental physics and do not have that much empirical contamination, let's say.
I see. So that's a unique choice of word. But aside from that, like what I gather is then that the trends you're talking about is that the models that we are using, or at least the collection of models that we are using coupled in this way, are capable of recreating scenarios that already exist, and thus we have some confidence that they can or at least predict what is going to happen inside scenarios that are not currently existing, right? Like, is that what you mean by a trend, or do you mean by a trend like if we increase density then this increases?
Yeah,
right?
okay, no, yes. So that the first, like the trend itself, I meant, yes, so connection between, I increase a certain parameters, what do the other parameters do? Like ideally, you can have it on engineering parameters, and then you turn valves in the control room, and then something happens to the plasma. So that you should be able to connect. But even the reason why I introduced the second topic of models is that even to get trends, you need this kind of modeling.
Mm-hmm. Okay,
so a trend in JET won't mean a trend in ITER, but a trend that is captured by the model in JET is a trend that will be probably true also in ITER.
So you're saying even if the exact like direction of the trend changes because of some specifics of this ITER reactor, then if the model did it right in a previous reactor, it's more likely that it will do it right.
It
even
should capture a trend.
Yeah.
Yes, exactly.
Even though the trend changes, but it will capture the change in the trend as well.
Exactly.
Or okay. So I guess coming down to it, I guess it's probably a very difficult question, but how uh, I guess how confident are we in the current models capability to represent ITER, considering ITER, this reactor in the south of France is still under construction as far as I know.
No, this is a great question, and also for whoever is listening to us, I don't think we are super confident. We are fairly confident in the sense we tried the model. It kind of works well in certain conditions, and then it's all building out of them. So you try to validate one model and then also other models which have different assumptions. Then you just clump them together, try to see how bad it is if you change the assumption, or if your assumptions are not really met. And you try to build confidence that what you're doing is good. First, like predict first modeling, as it's called, which is basically first I predict the experiment, and then I do the experiment and compare it back to what I predicted, is starting now, I think. Really is really taking off now that we can do this, and it would be very useful for ITER for sure, but I don't want to give the impression that we are absolutely sure of what will happen in ITER. If we were, we wouldn't need to build it.
Precisely, exactly. Yeah.
We would just, okay, fine, we know everything, we go to demo. But
So
we still need to build ITER to build all these and to continue the building of confidence and to optimization, precisely understanding what is going on.
Well, I guess one question is that do you think that that is a worthwhile final objective to have predict first modeling capabilities, or is it sufficient to say the model captures the physics that we know well enough, and then use the models to, let's say, delve into that physics, which I guess is closer to what you have been using them for, right? Like it seems to be that there are two use cases of a model, let's say. So is it worthwhile, or is it something that we have a model and then we build the machine and then they exist in separate realms, right?
Yeah, so in my opinion, it's gonna be worthwhile to build a predict first, but you also want the simplest thing that works. So you want to have your model the easiest, most simple thing that you can imagine, but it also has to work, which sadly Fusion is still a pretty complex model.
Right,
and
exactly.
with that is really it will be really useful, because with that you don't need to build another ITER to know what will happen. You don't need to run the scenario to know what will happen. You can explore many more possibilities and optimize much more effectively. So this is the real advantage. Once we have that, it's just price. You can build 1,000 machines, or you can have that.
Right, exactly. It doesn't take as much, let's say, both time and money to run a simulation as opposed to building an entire machine, right?
Yes, unless you are in TCV. So I was talking with some people at TCV the other day, and mentioning some really expensive simulation, which is on the edge part, which is more difficult and with very few assumptions, which means very long simulation time.
Okay.
And if the input on the simulation was wrong, it was actually cheaper to run an experiment with different parameters than to rerun the simulation.
Okay, so there are simulations in the field that are so expensive that it's on that side too.
Yes.
Okay. Well,
But
that's
okay, I mean that is on a funny note on small tokamaks and very large simulations.
well, but that's true, right? There's always a break-even point if it requires so much computing resources. Actually, it turns out that an experiment is cheaper.
Yes.
That's funny. But but then how, I guess, like, coming back to the original point about the predict first modeling, then how would you approach it, right? In how do we build a model such that it becomes predict first or has predict first capability, or do you foresee a certain pathway of combining all the information and expertise we have such that we can get a predict first model, but without too much without too much extra investment, quote unquote?
Okay, so the answer to this question is actually pretty complex in the sense that from my perspective, you kind of need to build from two parts, like from two sides. One is the really fundamental simulations, which is like with the ones that I was talking about, really expensive, huge simulations that don't really assume much. So you just take your system, you do the smallest amount of simulations of assumptions, so you're kind of sure that what you put there is correct. And then you run it and it's going to be absolutely huge and it's going to take a lot of time. And then you're going to have this one point in these specific conditions, which you will have an answer with. And then you want to go down and assume more. So, okay, what if this is not important and I can go faster? What if the other thing is not important? Of course, that thing might be important and might be important in some conditions, but you want a fast model.
Mm-hmm.
And then in the end, you will connect with the other side that is comparison of your model with the experiment. So a very simple model, you can compare it with the experiment, and then the validation process starts.
Mm-hmm. Yeah, so I guess maybe to explain what validation is, if you
So
could.
yes, so I mean with validation, I mean when you compare your model prediction with the experiment, and in the end you can say, okay, this actually is very close to the experiment. So all the assumptions I made are actually good in this case. So it works. I can use this fast model to predict what will actually happen in a much more complex system, but a lot of it is ignorable.
Okay. Yeah, so like in that sense, it's more, um, I guess the question is that if you so found out in this validation process that your model is insufficient in some reason or in some regime of plasmas.
Yeah, then you have to go up again in the
Mhm.
chain of assumption you made and understand, okay, where does it break?
Right. And I guess this is the process that is currently already happening
Yeah,
within the
of course.
community. But in some sense, what what we've seen, what I've seen, I guess, is that this process, this chain of going back and forth, up and down, is not extremely efficient, or has problems in communicating those requirements and constraints back up and down the chain. So from your aspect as someone who has also worked in this field, do you see any way of improving that type of feedback, let's say, between experiments and modelers and physicists?
So I think this is a relatively new topic. With relatively new, I mean a few years that we're actually able to do something like this. Before it was mostly other methods, which work, but not as well, in my opinion. Uh, no, but
what what methods are these? Well, I just asking, what methods are these?
it's just scalings. So
Oh,
they
scalings, yeah.
work incredibly well, but it's difficult to extrapolate. Basically, scaling, for whoever is listening to us, is um, you take the parameters and you build some sort of um, relation with with exponents, and that should have you fit them to the experiments, and then that should give you kind of the trend of the experiments with other engineering parameters.
Right.
Or
It's just
dimensional parameters are also used a lot. There's a whole work there which would take a lot of time to explain. They work surprisingly well. Like I was surprised, for example, with ITER. They did some scaling work quite a long time ago, and then they did the full simulations not that much time ago, very, very recent, and they agreed surprisingly well. Like it was actually correct, but it's still dangerous to extrapolate with scalings, especially if there's some specific regions of the parameter space that might be optimized and you will never find it with a scaling.
so I guess in contrast to the scaling, what is this new methodology?
So the
Is
new methodology is actually to try to model the full tokamak.
right. Okay. So it is what you were talking about to
Yes,
take these like advanced models and then
exactly.
distill them down into more simple models and then use it to compare against experiments.
Yeah, so since it's a decently recent method, I think all the infrastructure that will enable this to be done in a more consistent and systematic way is still not there. And also, Fusion is a large community, and a lot of people know a lot of different things. And while we do try to communicate through conferences and through meetings and et cetera, it takes time before all parts are aware of all the possibilities that are around.
Yeah,
So,
that's true. That's true. Like I guess in also my experience, the communication between even experts. I mean, we have email and the occasional conference, but it's really hard between all the busy schedules of everyone involved to actually coordinate, you know, something on this scale. Is
yeah,
that also in your experience,
no,
right?
that
Yeah.
definitely. But I kind of do understand where this is coming from, because it's Fusion. I don't know if in particular, of course, I'm biased because I work on it and then I learn a lot of it, and it seems huge, but it's really huge. And another thing that complicates the matter is that you need to know a little bit of everything to really um, have an idea what is happening, because the various parts of the system are really interconnected, and then all the experiments have and how the measurements are taken have a really deep impact on your modeling, and you just need to know a lot. So you need to meet a lot of people and to summarize everything in a nice, consistent way is a titanic task, I think. So I do understand where it's coming from. On the solution part, I am not sure I have them for you.
That's fair. I mean, like
It's not easy.
if the solution were easy, it would have been done, right? Like
Yes.
this is the way I always see these
Yeah,
things.
yeah.
But okay, but it is a challenge in the community then, also from your perspective
Yeah. No, I agree.
coordinate things at this level. Okay, but is there anything that you could say that would help at least at a very like a tiny bit make it a tiny bit better? Is there anything that you could advise, let's say, or things that would help you to coordinate better, right?
Mm, it's all I feel that we have all the tools, like we have the conferences, we try to do documentation. Maybe, okay, what could help is to reserve, let's say, part of the time of each researcher specifically to that. So, okay, don't do your own work for this part. Uh, just try to organize, because also, I mean, also the paper writing is meant to go in that way. The paper is a method to communicate.
And so are
And
the
then you end
conferences,
up,
right?
yeah, and but you end up with so much material that you can't read all the papers. So you
Ye-
try to read the ones that are useful for you, and still to have a overarching view of everything is not easy. So maybe we can think about a few solutions, but it's not an easy problem.
No, for sure not, because as you just mentioned, it's also that the expertise of the people is so wide and varied
Yeah,
and so deep also, right? So each scientist who's doing work in a specific field knows so much about that other scientists may not have the same level of depth in.
yeah,
So
and at the same time,
yeah.
on the other hand, everyone knows so little.
Exactly.
I
They know
always
their
have,
tiny
yeah, I
box.
always
Yeah.
have this feeling.
Mm.
Okay, I know this is little part, but then there's a huge amount of things that might help me, but that I don't know.
So there's also a danger that, like, even though you set this time aside for this communication to happen, that the communication will be a little will not be effective or not be used. That time won't be used to its full extent because a lot of it will be, you know, explaining context and explaining the details of why this is this way. um is that a danger, or do you think there is fundamentally some way to communicate that, to communicate what is important without having to basically teach someone the entirety of your field? Right.
No, that there has to be a way. I think it also comes with experience. You learn to have a more Hawkeye vision later when you interact more. I am still, of course, on the beginner side, but still, you see this problem at all levels. Like it's there, and it's kind of normal that it's there.
Well, but I
Uh,
think the conversation, even at this beginner level, because I'm at the beginner level too, let's be honest. But I think that this conversation at this level is also important because it's people at this level who will, you know, who do also a fair amount of the body of research and also will at some point in time move up the chain. So if you've thought about it, how it operates with us, and try to make it, you know, also give feedback currently, but also as you advance upwards, that you keep these ideas in mind, that you can kind of put them in place when you have the capability to, right?
yeah, no, for sure, it helps.
Yeah,
It
yeah.
helps planning and discussing about these kind of things, throwing ideas around, and always also, yeah, that what we're doing now, throwing ideas really around, like to a larger public, and
Mm-hmm.
see what the collective mind comes up with.
Yeah, exactly. And I think that was also one of the reasons behind the this podcast idea in the first place, is that we want to put these ideas out there, I guess, so that other people who might be thinking of the similar things, or at least might have wanted to try a solution but didn't realize other people were interested in it, are more encouraged to contribute, right? So yeah, that's true. But I guess in that same in that same line, is it is it something that you see that can be actually improved, or is it always going to be some sort of, or is the inefficiencies that are currently here sort of necessary simply because everybody is so specialized?
I
It's
don't
like,
think they're necessary. Uh, I do understand where they come from, but you of course can also, you can always improve. There there won't be a perfect solution or a perfect system for this, I think, but
mhm.
there can be improvement, and I think that there will be, in a sense that the community is kind of integrating in a more compact way. It's also getting larger, which is a problem.
Well,
But
I
is
one good thing about this whole I guess the time that was 2020, basically is that it put a lot of people online. So things like this kind of like Zoom meeting, offline discussion has improved dramatically. I think beforehand it was mainly conferences that I would meet anybody from outside my institute, right?
yes, no, that is true. The online life, the online community could be really useful for this, to build something more worldwide, because of course the fusion community is everywhere.
Yeah,
So,
yeah.
and every, like the whole world is working on this, so it can be very spread out, but online it's much easier to get to create an environment which is close. Like I can be close, I can just Zoom someone from the US and say, hey, I have this idea. Uh, that might be a very useful thing.
I guess one
Came
question
out
I
of 2020, just to give a positive
yeah,
note to this disaster of a year.
yeah, that's true. That's true. But one thing that I have to ask is that I guess in your times communicating through this medium, have you found any sort of or experienced any sort of channels of communication that were particularly effective, let's say, or particularly useful for you?
Hmm. Well, 1 versus 1 Zoom meeting are useful. And then the other thing I did was a lot of like presentations with question and answer, very standard. I wonder if one could introduce a different kind of way to do this, something more interactive. Like for example, yeah,
Hmm.
the thing we used uh, in our group, and you were also part, so but for the other people, this gather thing, which is basically um, online room or a set of rooms where you can actually go around with your little character and talk with people like you were in a room. So when there's like vicinity um, diagnostic in the program, and when you go close to the person, then your audio is connected to him. So it feels really like a room. And then you could kind of imagine if you get quite a few people and you try to structure a meeting in that environment, uh, it could be very effective, especially for people who live physically very far from each other. And then you just have this room or this set of room where you can go and talk with other researchers. That would be fun. That could be interesting.
Yeah, I know a number of other conferences also based in the US also try to use this gather in a full conference setting, sort of like to replace the conference. So normally in the
Oh,
conference you can just talk to this person and go grab a private room, but then they set it up that the but of course it was only for the social events, not for the actual conference itself. But yeah, one could I guess see that you could use a similar platform for the actual conference, right? So to have rooms where people present and then people can walk around and, you know, have private discussions on their own if there's nothing happening that is particularly interesting to them at the moment,
yes. You
right?
could envision even a more daily thing, to
Hmm.
have a few of these rooms where people can just go uh, in the community and talk within each other.
That
It
would
would be
be
fun
so it'd be sort of
thing.
like a virtual institute. Like
Yeah,
you'd like sign in for your day at work into this platform and then whoever's there you can talk to.
yeah. On the side of your normal work, you're also there.
Yeah,
I mean,
yeah.
if you're in the office, maybe it's a little bit more difficult because, of course, you need to talk and it gets a little bit crowded. But
Yeah.
especially working from home, if some work from home will last even past these uh, next few months, then you could think about setting up something like that.
Yeah, actually, that's an interesting question. I guess we're deviating completely from the scientific,
Yes.
but that's fine. That's part of that's the reason I set this up. But how do you think that the return to, on offline work will be like?
It would be so. It was weird for me to start this way of work always from home. Uh, at the beginning, for example, I needed to find a routine. So I wasn't as productive, and then it kind of settled down for me, and I went back kind of to normal, well, new normal. So I guess it will be similar going back. I will have to get used to normal working again. I, on one side, I do hope that a couple of days a week, or even just one day a week, the work from home will remain, because it works sometimes. Also, if you have to commute, it takes off some stress from the week, so that could be nice. And at the same time, I do want to go back to the office.
Hmm.
Uh, it is kind of a nice thing, like to go to the office, to have your routine, to go for the coffee, to eat with the colleagues, to
Even
have
just to
this kind
see
of,
people.
yeah.
Yeah.
I do miss it a little bit, so I hope that we'll be able to go back to the office at least one day a week relatively soon.
Yeah, but I can imagine having some sort of mix between offline and online type of work. So work from home and work from office would be ideal in some sense, because also me, I have had a huge boost in productivity because of the fact that I didn't have to do the commute, and there were certain, I guess, not necessarily luxuries but privacies offered by staying in the house, right? Like you
Yeah,
can
for sure.
really sit down and
The
focus.
the period of writing my thesis, also because of time limit stress, and you have to write the thesis. But being at home, it was literally something like 100% focus on that. So the productivity was completely insane.
Yeah, that's true. Like, and also like normally you have chores to do around the house, like just like cleaning, dishes, laundry, all this sort of stuff. Being working from home allowed you to do that while working. Whereas if I'm in the office, that's I can't come back and just do my dishes in the middle of the day, right? So like it's not feasible anymore. So it becomes, although I do have to say that the separation, I guess, of work and life by going to the office is
Yes.
also crucial in some aspect, right?
Yeah. I can live with a melted work life situation for a while, but not for too long. At some point, it's nice to have, um, you go to the office, you go out, and then you're out. Like the rest of the day, you don't do anything.
Mm-hmm, mm-hmm.
And that, yeah, but maybe because we were PhD students, so that's still a little bit more merged than other work situations. But it was probably a thing during this lockdown and working from home.
For sure. I
Merge.
yeah, for sure. I think there was a point for me also that it was like, yeah, you're working until like unseemly hours. Just because your computer is there, right? It's already on the websites or the programs that you normally work on. So why not check up on this simulation? Why not read this paper, right? uh
just the last paper. I know it's there. Let's
yeah. Super not the healthiest, not the
no.
healthiest attitude. I will say that for sure. But yeah. So for a little while I can see what you mean, but not forever. But I think it's also important to I guess communicate these sorts of things, because it's sort of not really known how much work happens outside of working hours, let's say, for a typical researcher.
I think it
It's
was like a forced experiment. So before you like the boss wouldn't say, okay, work from home, you're gonna be the same productive as ever. Yeah, I don't really know. Never tried to have someone work from a long time, and you don't know what is gonna do to the productivity. So you're you don't want to do that, so to let people work from home. And now that we know what happens because we had to, then maybe it's a little bit more acceptable. That's why I hope that a couple of like 1 or 2 days a week will be fine.
yeah, that it would be nice. It would be nice. I mean, I don't see why it would be necessarily problematic, but of course, yeah, we're not in any position to decide that. So, but I agree with you. It would be very nice if that were the case. Uh, okay, and I guess we're almost at the moment where I should be wrapping this up. I think we're at like 45 minutes in, but I guess I have one final question for you. Is do you have anything that you would like to promote that's upcoming either in your research or scientific career that you want to, or opportunity coming up that you'd like to tell everybody who's going to watch this?
So what I'm gonna do now uh, is so I finished here, almost finished here at differ wrote my thesis about all the things that I was talking about before. And now I'm gonna be part of a larger project that we started here in Europe. So I will go to Switzerland. And the idea here is very much in line with what we talked about. So it will be on this kind of modeling, validation of our modeling, and we'll try to um, use it also, maybe to plan some experiments and this kind of things. So in general, to this theme of trying to let people understand the options that are around, I do think that once this is uh, up and running, then we'll be able to help the community. And even that's also the dream of our supervisor, Jonathan, to help in the control room. So to say, okay, now to get this result, you change this parameter, you change the valve and you puff a little bit during this time. And then it works exactly how we predicted. So I do think, and I do hope that that capability is gonna come online. So this is my beat on what I think should be available to the community and to let you know,
And you're going to
let
be
everybody know.
obviously involved in that. So
I'm gonna be in there. I'm gonna be
great.
trying to set this up. This will be fun. I mean, if we can actually go in the control room and suggest what to do to the experimentalist, that would be awesome.
Yeah, well, and you're at least from my experience working with you, you're a great scientist and a fantastic plasma modeler. So it's good
Thank
to have
you.
you on the team. It's going to be
It's good to be on the team.
interesting. Yeah, it's going to be
Yes.
it's going to be a fun time. I think that's an exciting new times for plasma modeling in general. It's so good to have you there to be part of that.
Thanks.
And okay, so then thank you again for coming on board and having this discussion. I'm
Thank you
sure
for
there
inviting
will,
me.
no worries. It's a new initiative, so I think we had a very productive discussion, and I hope everybody found at least some value or insight or some renewed interest even in this type of communication, if not the field itself. And with that, I guess we'll sign off. Thanks everybody for joining, and we'll see you on the next episode.
Bye, everybody.
Bye.